we derived the equation for the root mean square value of the AC voltage and the AC current in the previous class. Today we are going to discuss the AC voltage across a resistor, an inductor, and a capacitor. So let us consider an AC voltage across a resistor. If you look at the circuit diagram, the AC voltage is applied across a resistor. There will be an AC current in the resistor, and the AC current result in a voltage drop across the resistor. If we apply KVL to this loop, according to KVL, the sum of the voltage rises in this loop will be equal to the sum of the voltage drop. So according to KVL, the voltage across the source will be equal to voltage across the resistor. Voltage across the resistor will be equal to voltage across the source. And we know that the AC voltage across the source varies sinusoidally with respect to time. So here is the time varying equation for the AC voltage. We want to find out the AC current in this resistor. Before the calculation of the AC current in the resistor, we consider the waveform for the AC voltage. So this is the waveform for the AC voltage across the resistor, and you see this AC voltage varies sinusoidally with respect to time. Now we are going to find out the current in the resistor. We know that the current in the resistor will be equal to voltage across the resistor divided by resistance of the resistor. This is how we compute the AC current in the resistor, and as VR is equal to Vs, so we can replace VR in this particular equation by Vs, and the current in the resistor of this AC circuit will be equal to Vs by R. What we do, we put the value of Vs in this particular equation. We know that Vs is an AC voltage, and this voltage varies sinusoidally with respect to time. So here is the instantaneous equation for this AC voltage. So let us put this value in the equation for the current. If we put this value in this equation for the current, the alternating current in the resistor will be equal to Vm by R sine of omega t, and Vm by R gives you the peak value of the current, the maximum value of the current. So the AC current in the resistor will be equal to Im sine omega t. So this is how we calculate the AC current in the resistor, and we know that the resistance of the resistor will be equal to the maximum voltage across the resistor divided by the maximum value of the current. So this ratio gives you the resistance of the resistor of this AC circuit, and is the AC current varies sinusoidally with respect to time. So we consider the waveform for the AC current in the resistor. This is the waveform for the AC current in this particular resistor. The maximum value of this current is represented by Im, and this maximum value is also known as peak value of the AC current. Now we are going to find out the power which is consumed by the resistor. So the power which is consumed by the resistor is equal to I square R. We put the value of the current in this equation. If we put the value of the AC current in this equation, so if we put the value of the current in this particular equation, the power will be equal to Im square into R into sine square omega t. This will be the equation for the AC power. The AC power which is taken by the resistor from the AC voltage source. And if we plot this AC power, the waveform for this AC power is shown over here. You see here is the peak value of the AC power, and this is how the power varies with respect to time. So one complete cycle of this AC power is from 0 to pi radian. So we want to compute the average value of this power. In order to compute the average value of this power, we integrate the instantaneous value of the power with respect to omega t from 0 to pi, and we divide this value by pi. So we use this equation to find out the average value of the AC power which is taken by the resistor from the AC voltage source. The resistor will consume this power. This power will be converted into heat energy. So the power taken by this resistor is equal to 1 over pi, the integration from 0 to pi of Im square R sine square omega t d omega t. The same equation can be written as the integration of sine square omega t d omega t from 0 to pi. And we know that sine square omega t is equal to 1 minus cos of 2 omega t by 2. So if we replace sine square omega t by 1 minus cos of 2 omega t, we obtain this equation for the average value of the AC power. The average value of the AC power is equal to Im square R by 2 pi, the integration from 0 to pi of 1 minus cos of 2 omega t d omega t. And the same equation can be written as Im square R by 2 pi. We have the integration of d omega t from 0 to pi and the integration of cos of 2 omega t d omega t from 0 to pi. And we know that the integration of the second term is equal to 0. So the integration of the second term results in 0. The power taken by the resistor will be equal to Im square R by 2 pi, and we have the integration of d omega t. The limits are 0 and pi, and we know that the integration of omega t is omega, the integration of d omega t is omega t, and the limits are 0 and pi. So if we simplify this integration, the average value of the power will be equal to Im square R by 2, and we know that the RMS value of the AC current is equal to Im divided by under root 2. So if we replace Im square by 2 by I square, then the average value of the AC power taken by this resistor from the AC voltage source will be equal to I square R, where I represent the RMS value of this AC current. Let us consider AC voltage across an inductor. So we apply an AC voltage across an inductor. There will be an AC current in the inductor, and this current results in an AC voltage drop across the inductor. If we apply KVL to this loop, according to KVL, the sum of the voltage rises in this loop is equal to sum of the voltage drops, and the voltage across the inductor will be equal to voltage across the source. So Vs is equal to VL. This is in accordance with KVL. And the equation for the AC current is given over here. The AC current is equal to Im sine omega t. So we can consider the waveform for the AC current. Here is the waveform for the AC current. We know that the magnitude as well as the direction of the AC current changes. The magnitude as well as the direction of the AC current change with respect to time. So the AC voltage across the inductor is equal to L di by dt. So we can find out the AC voltage across the inductor with the help of this equation. So let us put the value of the AC current on the right hand side of this equation. If we differentiate the value of the AC current with respect to time, let me go back and let me explain this derivative. So we know that the equation for the AC current is, we have the maximum value of the current into sine of omega t, and if we differentiate this current with respect to time, we will get the maximum value of the current into omega L into cos of omega t. So this will be the AC voltage across the inductor. So the AC voltage across the inductor is equal to the maximum value of the AC current into omega L cos of omega T. And maximum value of this AC voltage, the maximum value of the AC voltage across the inductor is equal to the maximum value of the current omega L. So omega L will be equal to the maximum voltage across the inductor divided by the maximum value of the current, and this quantity gives you the resistance of the inductor. This is the resistance which is offered by an inductor to the flow of AC current, and the resistance which is offered by an inductor to the flow of AC current is known as inductive reactance. The inductive reactance is represented by XL. XL is equal to omega L, and omega L will be equal to 2 pi FL. So this is the inductive reactance of the inductor. If we apply a DC voltage across the inductor, we know that the frequency of the DC voltage is 0. So the inductor does not offer any resistance to the flow of DC current. The inductive reactance of the inductor for the DC voltage is 0. So the AC voltage across the inductor is equal to maximum value of the current XL cos of omega T, and cos of omega T can be written as, so cos of omega T can be written as we have sine of omega T plus 90 degree. So the voltage across the inductor is equal to the maximum value of the current into XL into sine of omega T plus 90 degree. This equation indicates that the voltage across the inductor leads the current by 90 degree. In other words, the current in the inductor lags behind the voltage by 90 degree. In other words, there is a difference of 90 degrees between the voltage across the inductor and the current. So we consider the waveform for the AC voltage. Here is the waveform for the AC voltage across the inductor, and you see the AC voltage across the inductor leads the current by 90 degree. You see the AC current starts from over here. So if this is the waveform for the AC current, you can see that the waveform for the voltage across the inductor leads the current by 90 degree. So voltage across the inductor leads the current by 90 degree. In other words, the current in an inductor lags behind the voltage by 90 degree. We want to find out the power taken by the inductor. So the power taken by the inductor is equal to VLI. We put the value of VL and I on the right hand side. So here is the value of the voltage across the inductor, and here is the value of the current in the inductor. If we simplify the right hand side of the given equation, the power taken by the inductor is equal to Im square XL sine omega t cos of omega t, and we know that sine of omega t cos of omega t is equal to sine of 2 omega t by 2. So the time varying equation for the power taken by the inductor is equal to Im square XL by 2 sine of 2 omega t. And if we plot this equation with respect to omega t, we get the waveform which is the waveform for the AC power taken by an inductor, the peak value of this power is Im square XL by 2, and the positive half cycle is from 0 to pi by 2, the negative half cycle is from pi by 2 to pi. So anyhow, we want to calculate the average value of this AC power. So the average value of this AC power will be equal to 1 over pi. Then we have the integration from 0 to pi of the instantaneous value of this power, and the instantaneous value of this power is Im square XL by 2 sine of 2 omega t d omega t. The same equation can be written as, we have the average value of the AC power taken by the inductor, which is equal to Im square XL by 4 pi, and then we have the integration of 2 sine of 2 omega t d omega t, and the integration of 2 sine of 2 omega t d omega t is minus cos of 2 omega t. And if we put the values of the limits in this particular equation, the average value of the power taken by the inductor is 0. So the inductor does not consume power under ideal condition. The resistor consumes power. It converts this power into heat energy. The heat energy is dissipated in the surrounding atmosphere, but the AC power taken by the inductor is the average value of the AC power taken by an inductor is always equal to 0. The inductor does not consume any power under ideal condition. We consider AC voltage across a capacitor. So let us apply an AC voltage across the capacitor. The AC voltage across the capacitor results in AC current, and this AC current results in a voltage drop across the capacitor. If we apply KVL to this loop, according to KVL, the voltage across the capacitor is equal to voltage across the source. The current, the AC current in the capacitor is equal to Im sine omega t, and here is the waveform for the AC current in the capacitor. We know that the alternating current changes with respect to time. The magnitude as well as the direction of this AC current change with respect to time. So here is the waveform for one complete cycle of the AC current in the capacitor. If you want to find out the AC voltage across a capacitor, you guys can use this equation. The voltage across the capacitor is equal to 1 over C, the integration of di by dt. And if we integrate the AC current with respect to time, you see here is the AC current. The AC current varies sinusoidally with respect to time. So we have Im sine of omega t. We have Im sine of omega t. So if we integrate this current with respect to time, this integration will give you minus Im by omega into cos of omega t. So anyhow, we can find out the the AC voltage across the capacitor. With the help of this equation, we integrate the current with respect to, well, this equation is incorrect, right? Yes. This equation is incorrect. So the voltage across the capacitor is equal to the 1 over C and the integration of I dt. So if we integrate the current with respect to time, the voltage across the capacitor is equal to minus Im by omega C into cos of omega t. And you see the maximum value of, here is the maximum value of this AC voltage. So the maximum value of this AC voltage is equal to the maximum value of the current by omega C. This gives you the maximum value of the AC voltage across the capacitor. So 1 over omega C will be equal to the ratio on the right hand side. We have the ratio of the maximum value of the AC voltage across the capacitor to the maximum value of the current, and this ratio gives you the unit of ohm. So this is the resistance which is offered by a capacitor to the flow of current. So the resistance which is offered by a capacitor to the flow of AC current is known as capacitive reactance. Capacitive reactance is equal to 1 over omega C, and 1 over omega C is 1 over 2 pi Fc. If you apply a DC voltage across the capacitor, the capacitive reactance will be infinity, and this means that the capacitor will be have like an open circuit for the DC voltage. There will be no flow of current. So anyhow, the voltage across the capacitor is equal to minus the maximum value of the current into Xc into cos of omega t, and we know that minus cos of omega t is equal to sine of omega t minus 90. So the voltage across the capacitor is equal to the maximum value of the current into Xc into sine of omega t minus 90. So this equation shows that the voltage across the inductor lags behind the current by 90 degree. In other words, the current in a capacitor leads the voltage by 90 degree. This is the voltage across the capacitor with respect to omega t, and you see that the voltage across the capacitor lags behind the current by 90 degree. Why? Because if you consider the waveform for the AC current, it will be something like this. Okay, so the voltage across the capacitor lags behind the current by 90 degree. We want to calculate the power which is taken by the capacitor from the AC voltage source. So we can compute this power with the help of this particular equation. If we put the values of the voltage across the capacitor and the current on the right hand side, we get this particular equation. And if we simplify this equation, the power taken by the capacitor is equal to minus Im square Xc sine of omega t cos of omega t. So the power taken by the capacitor is equal to minus Im square Xc by 2 sine of 2 omega t. And if we plot this last equation, so we get the waveform for this AC power. The AC power which is taken by the capacitor from the AC voltage source. Here is the peak value of this AC power. Here is the maximum value of this AC power. So we want to compute the average value of this power. So we integrate the instantaneous value from 0 to pi, and we divide it by pi. So PC is equal to 1 over pi. Then we have the integration from 0 to pi of minus Im square xc by 2 into sine of 2 omega t d omega t. The same equation can be written as, we have minus Im square xc by 4 pi, and then we have the integration of 2 sine of 2 omega t d omega t, and we know that the integration of this quantity results in minus cos of 2 omega t. If you put the values of omega t, the values of the limit in this particular equation, the average value of the AC power taken by the capacitor is equal to 0. So the capacitor does not consume AC power under ideal condition. The average value of the AC power is equal to 0.